So hello everyone, my name is Varad Daoo and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and also a Prime Minister Research Fellow at the same department. So I welcome you all to this third lecture, to the fourth lecture of Structure of Atom. Let me write this down. So up till now, in the last class, what we have covered is, we have covered that there exist certain rays called as cathode rays, and the particles consisting of them are negatively charged, and these particles are termed as negative. And it was also after the discovery of this cathode rays, it was hypothesized that as the atom in overall is a neutral molecule, there must be positive particles, positive subatomic particles as well. This was also discovered by uh, by Professor Goldsmith in around 1809, and these particles were called as protons, and the rays consisting of these particles were called as anode rays. So we have studied about the experiment which was done to perform to discover these anodic rays. Further, we have also seen the characteristics of these anode rays. Further, we have also seen that how these electrons and protons, that is the subatomic particles, are arranged in inside the atom. So for that, we have studied many couple of models. So first was the J.J. Thomson's atomic model, right? Where a sphere and negative charges are embedded in it. So this model was also called as plum pudding or watermelon model. However, this model suffered with some. However, this model was not able to explain the experimental observation observed by the Rutherford. So so we have studied this Rutherford model as well, and the experiment which was done by Rutherford to give this model. This we have studied in detail, and then we have also studied the drawbacks and advantages of Rutherford's model. Right. So now, up till now, what we have considered is we have considered atom as a particle, and the subatomic particles, that is electrons and protons, are also particles. However, this is not the case. After the discovery of after the Rutherford experiment, there have been significant progress in the field of physics, like Young's double slit experiment or Einstein theory of photoelectric effect, which stated that subatomic particles are not only particles but they behave as wave. That means these subatomic particles uh, have a dual identity. That is, in some case, some behavior shown by these particles could be explained by considering that these are particles, whereas some other uh, 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 observations or the properties of these particles could only be explained by the waves. So in this class, what we are going to study, we are going to study what are waves, and then we are going to connect the wave theory with the particle theory, right? So during the period of development of new models to improve Rutherford's model of an atom, two new concepts played a major role. These are the dual behavior of electromagnetic radiation. This means that the light has both particle and wave-like properties. And number two, atomic spectra. The experimental results regarding atomic spectra of atom can only be explained by assuming quantized, that is fixed electronic energy levels in atom. So let us briefly learn about this concept, right? So let me first write this down. Number one, 12. So let me write this down. During the period development of new models, Rutherford's model of an atom, two new concepts played a major role, right? These are dual behavior of electromagnetic radiation. Light has both particle and wave-like properties. Number two, atomic spectra. The experimental results regarding atomic spectra of atoms can only be explained by observing quantized, that is fixed electronic energy levels in atom, right? So the next topic is nature of light and electromagnetic radiation. So we are going to study about the wave terminology and in discuss detail what are waves and what are its properties, right? So nature of light and electromagnetic radiation. So the earliest view of light due to Newton regarded light as made up of particles, commonly termed as corpus of light. The particle nature of light explain some of the experimental facts such as reflection and refraction of light. However, it failed to explain the phenomena of interfaces and interference and diffraction. Right? That is a double slit experiment which you will be studying in your physics class. The corpuscular theory was therefore disregarded and a wave-like character of light was proposed. With the help of wave theory of light, scientists explained the phenomenon of interference and diffraction. Right? So let me write this down. The earliest view of light due to Newton regarded light as made up of particles, right? Commonly termed as corpuscles of light. The particle nature of light explain some of the experimental facts such as reflection and refraction of light, right? However, it failed to explain the phenomena of interference and diffraction. The corpuscular theory was thus discarded, and scientists proposed wave-like character of light, right? So now let us understand about the wave motion. So let me first draw the diagram of ray. So this is called as crest. This is called as throw. This is what is called as wavelength. Distance between two crests or two trough is called as, this position is called as crest. So this position is called as crest. This position is called as crest. Whereas this thing, this is called as amplitude, right? It's called as amplitude, right? So all of us are familiar with the waves on the surface of water obtained by throwing a stone into the quiet pond. The waves originate from the center of disturbance and propagate in the form of up and down movements. The point of maximum upward displacement is called as crest, while the point of maximum downward displacement is called as trough. Thus, waves may be considered as disturbance which originate from some vibrating source and travel outwards as a continuous sequence of alternating crests and troughs. Right? Let me write this down. So wave, right? So wave maybe. So wave is considered wave is considered as disturbances which originate from some vibrating source and travel outwards as a continuous sequence of crests and troughs. Right? So now what is crest and trough? Right? So let us write this down. The point of maximum upward displacement is called as crest, and the point of maximum downward displacement is called as trough. Right? Let me highlight down. Upward is called as crest, whereas downward is called as trough. Right? So now let us study the characteristics of wave motion. Right? So all waves are characterized in terms of their wavelength, frequency, velocity, and amplitude. Right? So these are discussed below. Right? So number one, wavelength. Denoted by lambda. So the distance between two adjacent crests or troughs is called as wavelength. It is denoted by the Greek vector lambda and is generally expressed in terms of angstrom unit. Right? It can also be expressed as micron, millimicron, nanometer, or picometer. Right? So the distance between and crest or troughs. Right? Second is frequency denoted by mu. Right? So the number of waves which pass through a given point in 1 second is known as frequency. It is denoted by the Greek per view, and the units of frequency are cycles per second. Right? Right? And the units The units of frequencies are cycles per or simply reciprocal of second. Reciprocal of seconds. Second inverse, right? So 1 hertz is equal to 1 cycle per second. Right? The third is velocity denoted by c. Right? The distance traveled by a wave in 1 second is called velocity of the wave, and it is generally denoted by letter c and expressed as meter per second. Right? It is generally denoted by this symbol and is expressed as meter per second. Right? The fourth is amplitude, also called as a. It is the height of crest or depth of throw of a wave and is generally expressed by the letter A. The amplitude of the wave determines the intensity or brightness of the radiation. Height of crest or depth of throw of a wave and is generally expressed by the letter A. Right? The amplitude of the wave determines the intensity or brightness of the radiation. Right? The fast is wave number. Right? So it's denoted by mu bar. Right? It is defined as the number of wavelengths per centimeter and is equal to the inverse of wavelength expressed in centimeter. Right? It is denoted by mu bar, right? And is expressed in centimeter inverse. Right? It can also be expressed as meter inverse in SI unit, right? So wave number is nothing but inverse of wavelength. Which means mu bar is 1 by lambda. Okay. The relationship between wavelength, wave number, frequency, and velocity are right. So these are which is to be remembered, right? So C is equals to lambda into V, right? This implies V is equals to C by lambda. This implies V is equals to C mu bar. Excuse. Right? So see, so these are the relationship between the velocity, wavelength, frequency, and wave number. Right? So next topic is electromagnetic radiation and its characteristics. Characteristics. Right? So in 1870, James Clerk Maxwell proposed that light and other forms of radiant energy propagate to space in the form of waves. These waves have electric and magnetic field associated with them and are therefore called as electromagnetic radiations. Right? So let us understand its characteristics. So the first one is, these consist of electric and magnetic fields that oscillates in direction perpendicular to each other and both are perpendicular to the direction in which the wave is traveling. Right? The true field components have the same wavelength and frequency. Right? So these consist of electric and magnetic field that oscillate in the direction perpendicular to each other and both are perpendicular to the direction in which the wave is traveling. Right? The two field components have same wavelength and frequency. Right? Second is, all the electromagnetic waves travel with the same speed. In vacuum, the speed of all types of electromagnetic radiation is 3 into 10 to the power 8 meter per second. This speed is called the speed of light. Right? All electromagnetic waves travel with the same speed. Right? In vacuum, the speed of all types of electromagnetic radiation is 3 into 10 to the power 8 meter per second. So to be precise, the exact speed is 2.997925 10 to the power 8 meter per second. Right? This speed is called as speed of light. The third point is, these electromagnetic radiations do not require any medium for propagation. Right? For example, light reaches us from the sun through empty space. Right? So these electromagnetic radiations do not require any medium for propagation, right? For example, light reaches us from the sun to empty space, right? So now let us learn about the electromagnetic spectra, right? Let me draw an image. So as already discussed, all electromagnetic waves have the same speed, that is 3 into 10 to the power 8 meter per second. However, the different types of radiation differ from one another in their wavelengths and therefore in frequency. Thus, electromagnetic radiations with a long wavelength has low frequency, while the radiations with short wavelength has large frequency. Right? The complete range of electromagnetic wave is called as electromagnetic spectra. Electromagnetic spectra. Right? The electromagnetic radiation with a long wavelength has a low frequency, while radiation with short wavelength has a large frequency. The complete range of electromagnetic wave is called as the complete range of electromagnetic spectra, right? Thus, the arrangement of different types of electromagnetic radiation in the order of increasing wavelength or decreasing frequencies is called as electromagnetic spectra, right? The arrangement of different types of electromagnetic radiation in order of increasing wavelength or decreasing frequency is known as electromagnetic spectrum, right? So this is the complete electromagnetic spectrum, right? This is the complete electromagnetic spectrum. So there are various regions of this spectrum, right? So it is interesting to note that the visible light, the visible spectrum, which human eye can detect, constitutes only a small portion of total electromagnetic spectrum. The visible spectrum is also shown separately, right? This is the visible spectrum. Different colors in the spectrum correspond to waves of different wavelengths and frequencies. Out of the various colors in visible range, violet color corresponds to radiation of maximum frequency, that is 7.5 into 10 to the power 14 hertz, and minimum wavelength, that is 380 nanometers, while the red color corresponds to radiation of minimal frequency, that is 4 into 10 to the power 14 hertz, and maximum wavelength, that is around 760 nanometers. The frequencies and wavelength of the radiation corresponds to the color in between, lie between these two extreme values, right? The frequencies and wavelength of the radiations corresponding to colors in between lie between these two extreme values, right? The region just above the visible portion in the ultraviolet region, that is around 10 to the power 6 hertz of the spectrum. These radiations are included in sun's rays, although these are invisible. Beyond ultraviolet radiation, on the side of increasing wavelength, that is decreasing wavelength, increasing frequencies, that is decreasing wavelength, we have a region of X-rays, right? So these are X-rays with a frequency of around 10 to the power 19 hertz, right? 18 to 19 hertz. These rays, these are produced when a stream of electrons strike a heavy metal target. Beyond X-rays comes the gamma rays. So these are the gamma rays that originate from radioactive substances, and then are the cosmic rays, right, which originate in outer sphere and continuously fall on Earth. The portion below the visible region, that is decreasing order of frequency, right, is alpha red region, that is around 10 raised to power 13 hertz. These produce high thermal effects and is heat radiation, right? So this is infrared is nothing but heat radiation. These are used in telephone circuits and for radar. Below this region lie the radio waves or the mic. So these are radio waves around 10 raised to power 6 hertz, which have the lowest frequencies or highest wavelength RNR and are used for broadcasting. Thus, while radio waves have the lowest frequency or highest wavelength, the cosmic rays have the highest frequency or the lowest wavelength. The different types of radiations are arranged in decreasing order of frequency or increasing order of wavelength as cosmic rays, then gamma rays, then X-rays, then ultraviolet rays, right? And ultraviolet radiation, then visible radiations, infrared radiations, right? And microwaves, and finally radio waves, right? So based on this, let us solve some problems, right? First question: yellow light emitted from a sodium lamp has a wavelength of 580 nanometer. Calculate the frequency and wave number of this light. Okay. So solution: wavelength of yellow light, which is denoted as lambda, is nothing but 580 nanometer, which is 580 10 raised to power minus 9 meter, because 1 nanometer is nothing but 10 raised to power 9 meter, right? So we know that frequency is related to wavelength as lambda into V is equals to C, or C is equals to, or V is equals to. So this is basically mu, right? Mu is equals to C by lambda, right? Where C is velocity of light, which is nothing but, for all practical purposes, we take it as 10 into 10 to the power 8 meter per second. Hence, mu is equals to 3 into 10 raised to power 8 meter per second divided by 580 10 raised to power 9 meter, which implies mu is equals to 5.17 10 raised to power 14 second inverse, right? Again, we know that wave number is nothing but u bar is nothing but 1 by lambda, which is 1 by 5.17 10 raised to power 14 second inverse, right? This implies wave number is nothing but 1.72 10 raised to power 6 meter inverse, right? Right? So this is meter, right? Hence, what we have is its frequency is 5.17 into 10 raised to power 14 second inverse, whereas its wave number is 1.72 into 10 raised to power 6 meter inverse, right? So we'll move on to the next question. Right? So question number 2. A certain radio station broadcasts on a frequency of 980 kilohertz, right? What is the wavelength of electromagnetic radiation broadcast by the radio station, right? So what we are given is, we are given the frequency of the radiation emitted is mu, which is nothing but 980 kilohertz, which is 980 into 10 raised to power 3 10 raised to power 3 hertz, which is nothing but 980 into 10 raised to power 3 second inverse, right? Now we know that lambda into V, lambda into mu is nothing but C. That implies lambda is equals to C by mu, where C is equals to speed of light, that is 3 into 10 raised to power 8 meter per second. Hence, lambda is equals to 3 into 10 raised to power 8 meter per second divided by 980 10 raised to power 3 second inverse, implying lambda is nothing but 306 meter, right? Thus, wavelength of radio wave, wavelength of radio wave broadcast by the station is 306 meters, right? Okay, so let us move on to the next question, which is question 3. The wavelength range of the visible spectrum extends from violet, which has a frequency wavelength of 400 nanometer, to red, which has a wavelength of 750 nanometers. Express these wavelengths in frequencies. That is hertz, right? So what we are given is wavelength of violet light, nothing but lambda, which is 400 nanometers, 400 10 raised to power minus 9 meters. So what we have, frequency is related by this expression, where c is the speed of light, right? And its value is 3 into 10 raised to power 8 meter per second, right? Hence we can write mu is equals to c by lambda, which is 3 into 10 raised to power meter per second divided by 400 10 raised to power minus 9 meter, implying mu is nothing but 7.5 10 raised to power 14 hertz, right? So this is for violet light, right? Now for red light, what we have is wavelength of red light lambda is nothing but 750 nanometers, which is nothing but 750 10 raised to power minus 9 meter, right? So frequency, which is nothing but mu, which is c by lambda, is 3 into 10 raised to power 8 meter per second divided by 750 10 raised to power 9 meter, which implies mu is equals to 4 into 10 raised to power 14 hertz, right? Thus the range of visible spectrum in terms of frequency is from 7.5 10 raised to power 14 hertz to 4 into 10 raised to power 14 hertz, right? So with this, we conclude today's class. So what we have learned in this class is we have studied about what are waves and its characteristics. Further, we have also studied about the electromagnetic spectrum, and we have also solved a couple of examples on electromagnetic spectrum, right? So in the next class, what we are going to study are the particle nature of electromagnetic radiations and Planck's quantum theory, that is the black body radiations and Planck quantum theory of radiation, right? We are also going to study the photoelectric effect proposed by Einstein, right? So with this, I thank you all for attending this class, and I hope to see you again in the next class. Thank you.